Hello, we are Group 2, Team GMI, Great Mind and Cooperation. Group members Izzuddin, Fikri, Anis, Norfahda and Farah. For the integrated project, the question required us to design distillation units to recover 98% toluene from given 1000 kg per second feed mixture of toluene, benzene and xylene. We come up with this design using two distillation units in series. In Unit 1, we can see the flow rate 1000 kg per second, temperature at 85 degrees Celsius, and pressure at atmospheric pressure. The overhead stream is connected to a condenser, then to storage tank, while bottom stream connected to the second unit. In Unit 2, the inlet flow is 108 kg per second, temperature at 120 degrees Celsius, and pressure also at atmospheric pressure. The overhead stream connected to a condenser unit, then to the storage tank, while the bottom stream is directly connected to the storage tank.
For my part, I will explain a brief about the concept of the system. So as we can see already from the flowchart that we have drawn, we can see that it is a multiple unit since there are two distillation units that are connected together, which both consist of a feed stream, overhead product and also the bottom product. The overhead product of a distillation unit usually consists of a species that have lower boiling point, while the bottom product will consist of a species that have higher boiling point. Therefore, in order to find the overhead product and also the bottom product of a non-reactive system, we must first determine the independent equation and the unknown to find the degree of the freedom of the system, so that we can know if the problem is solvable or not. After that, by assuming the basis of the process, we can use the concept of the conservation of mass to find, which states that the total mass input is equal to the total mass output to find the product of both units.
We're gonna explain calculation part step by step. Our assumption for the temperature of benzene is 80.1 degrees Celsius, for the toluene is 110.6 degrees Celsius, and for the xylene is 139.10 degrees Celsius. For the first distillation column, DOF is found to be 0, means the problem is solvable as the unknown variables is 5, which are M2, M3, E, F and G, while there are 5 independent equations as stated. The overall independent equation is M1 equal to M2 plus M3. Then the specific independent equation for the toluene is Bt times M1 equal to Ft times M3. And the specific independent equation for xylene is Cx times A1 Cx times M1 equal to Gx times M3. Then the additional equation 1 is E plus F plus G equal to 1, and the additional equation 2 is equal to 0.96 times M1 times AB equal to AB times M2. First, mass flow rate for the feed 1 is 1000 kg per second. Then it's gonna produce top and bottom product. So the mass fraction in the feed AB equal to 0.2 kg benzene per kilogram. For the toluene, Bt equal to 0.30 kg toluene per kilogram. And for the xylene is Cs equal to 0.50 kg xylene per kilogram. So, based on our calculation, mass flow rate of the benzene in the first distillation is M1 equal to 200 kg per second, and M2 equal to 192 kg per second, and M3 equal to 808 kg per second. Besides, mass flow rate for the toluene is M1 T equal to 300 kg per second, and M3T equal to 300 kg per second. And the mass flow rate for the xylene is M1X equal to 500 kg per second, and also for the M3X equal to 500 kg per second.
Let's move to the second distillation column, in which DOF is also 0. So the problem is solvable. The unknown variables are 5, which are M5, M4, JK and L. There are also 5 independent equations for this part as stated. The overall independent equation is M3 equal to M4 plus M5. The value gained from the overall independent equation is M5 equal to 508 kg per second. And from the additional equation, M4 is equal to 300 kg per second. Then the mass fraction of benzene gained from specific independent equation is 3.94 times 10 to the power of -3. The mass fraction gained from a specific independent equation from xylene is 0.98 kg x per kilogram, and the mass fraction of toluene from the additional equation 1 is 0.016 kg T over kilogram. The mass flow rate benzene is M3 equal to 7.99 kg per second, and the M4 is equal to 6 kg per second, and the last one is M5 equal to 2 kg per second. The mass flow rate for the toluene M3T equal to 300 kg per second, M4T equal to 294 kg per second, and M5T equal to 8.13 kg per second. The mass flow rate of xylene M3X equal to 500 kg per second, and M5X equal to 597.84 kg per second.
For justification, there are some elements that we applied in our research on this problem. Based on the boiling point allocated for each unit, it shows the outcome of each recovery. Each column should have main product for each outlet, like in the calculation shown. Upstream in Unit 1 has 96% efficiency of benzene. Downstream of Unit 2 has 98% efficiency of xylene, and finally upstream of Unit 2 recovered in amount of 98% efficiency of toluene, which meet the requirement of the question. As we consulted with our lecturer, Dr. Teo Tamling, it is impossible to gain 100% purity from any process unit. Therefore, all the percentage calculated justified by reference given aromatic compound can be distillate up to 99% of purity. However, the distillation process needs to use reflux and some other ordinarization addition. For a basic demonstration, this calculation is enough to demonstrate principle of chemical engineering in separation process. Also, both Unit 1 and 2 product stream is connected to condenser, so the void gas streams is condensed back to liquid for easier storage. The condenser connection is as shown in the diagram.